A slurry can pass through a bead mill for hours, yet its final particle distribution is decided in collisions too small to see. Zirconium silicate beads convert agitator motion into repeated compression, shear, and impact between suspended particles. Their purpose is not simply to occupy the chamber. They form the moving contact network that performs wet grinding and dispersion. Smaller beads create more contacts within the same chamber volume, while larger beads carry more energy per collision. The useful size is there for a process decision tied to feed size, target fineness, slurry viscosity, rotor speed, and the mill separation screen. This grade combines zirconia, silica, and a smaller alumina fraction in a sintered zirconium silicate ceramic. The reference composition is 58 to 65% zirconia, 30 to 37% silica, and about 5% alumina. Composition and firing control determine the final microstructure, so material identity should be confirmed by specification rather than appearance. Zirconium silicate belongs to the medium density range of ceramic grinding media. A representative specific weight is about 4.1 kilograms per cubic decimeter, with bulk density near 2.4 kilograms per cubic decimeter. That mass supports useful stress transfer without automatically imposing the higher inertia of denser media. Hardness and fracture resistance matter because every chipped fragment becomes an uncontrolled solid in the slurry. The reference grade exceeds 900 Vickers hardness, while an independent commercial grade reports about 1000 HV10. A wear rate below 0.05 kilograms per ton of processed slurry is specified for this grade, but actual wear still depends on mill speed, formulation abrasiveness, and chamber materials. Inside an agitator bead mill, the rotor accelerates the media and the liquid phase carries particles through the bead bed. Each contact transfers only a small amount of energy, but the process produces a very large number of stress events. Milling performance therefore depends on both collision intensity and collision frequency, not on bead hardness alone. Reducing bead diameter increases the number of media pieces and usually raises the number of particle contacts within a fixed filling volume. Increasing diameter raises the mass of each bead and can increase single collision stress energy. Neither direction is universally better. Research on stirred media milling shows that bead size interacts with speed, viscosity, and material response, so selection must follow the complete process window. A stable milling setup matches bead diameter and density to the agitator geometry, separator gap, slurry viscosity, solids loading, and target particle distribution. Beads that are too small may challenge the separation system, while beads that are too large can reduce contact frequency or increase power demand. Screening, replenishment, and inspection must preserve the intended size distribution during production. For zirconium silicate media used in disc-type agitator mills, a common engineering range runs from 0.4 to 2.5 mm in closely controlled bands. The reference family follows that progression through sizes such as 0.4 to 0.6, 0.8 to 1.0, and 2.2 to 2.5 mm. The correct band depends on the mill and the required particle size. Extended diameters from 2.5 to 10 mm are available within this product family for coarser grinding or different equipment arrangements. A non-standard request should define nominal diameter, allowable size distribution, total charge, mill type, separator clearance, slurry composition, and target fineness. Custom sizing is useful only when the media remains compatible with the mechanical and hydraulic limits of the system. In water-based coating production, pigment agglomerates must be broken down without allowing coarse clusters to remain in the film. Medium-density zirconium silicate beads supply repeated stress events in low to medium viscosity slurries, making them suitable for general pigment dispersion. Bead size is selected so the contact network can reduce agglomerates while maintaining circulation through the mill. Media wear matters in coatings because bead-derived fines can alter color, gloss, filtration behavior, or downstream cleanliness. A hard, well-sintered spherical surface helps the media retain its geometry during repeated circulation. The specified wear rate below 0.05 kilograms per ton provides a reference for this grade, but validation should use the actual pigment, binder, mill lining, and operating speed. Round media and a controlled size band support predictable packing and movement through the chamber. In coating dispersion, that consistency helps maintain repeatable stress exposure as the slurry recirculates. The beads remain visually simple, but their diameter, density, surface condition, and wear behavior collectively shape the milling environment. Across millions of controlled contacts, each sphere becomes part of the process surface that determines dispersion quality.